camps. We're very happy to be hosting live with us Professor Maciej Dunajski, who is visiting us from the Department of Applied Mathematics and Theoretical Physics in Cambridge. He is an TIA fellow, part of a scheme which is put together in collaboration between the London Mathematical Society and camps, a collaboration which is honoring the legacy of Sir Maciej. And the scheme has two components, UK-Lebanon component and the Lebanon-UK component. And we were delayed in acting on this scheme in view of COVID and lockdown. And we're very happy to have with us Maciej as one of the first APIA fellows to visit us in person. So he's with us for the week, delivering a mini course on the calculus of radiation. Today, he gave the first live installment of the course and continue for the week. He intends and will be very happy to visit the math departments and as well as welcome colleagues and students. So all are welcome to contact our officer and arrange to visit with Maciej. During his visit, he's offered to give us an overview for a wide public of 4 facets of geometry, subject he is intimately familiar with in view of his expertise in differential and projective geometry, what he's done on solid and general relativity. I'm particularly pleased to have him with us today. And before concluding, I just want to thank my colleagues, Professor Florian Bertrand, the math department, and Professor Ayman Kashmar and Fida El-Shami from the Lebanese University, who helped coordinate the visit with students and colleagues in the various departments. Thank you all, and I hope you enjoy the talk. Thank you, Maciej.
Thank you, Jihad, for this kind introduction. So this is indeed going to be a very elementary invitation to geometry, and the title for Facets of Geometry. My intention is to present geometry from 4 different perspectives, starting perhaps from the oldest, from Euclidean geometry, but just to set up the scene and the subject, a good starting point I thought would be the Great Pyramid of Giza, which has been with us for, for well over 4,500 years, and it's a pyramid, also regular patterns here, and you know, it's been around for long enough for people to have a very close look at it and take measurements and come to conclusions. And one observation made by somebody was that if you take the circumference of the base of this pyramid and you're divided by the height of the pyramid, then you'll get up to 2 digits accuracy. You get the value of pi. So if that was the case, there's suggestion that the Egyptians knew about pi well before the Babylonians, the Mesopotamians, and the Greeks. Well, another observation somebody made is if you take the length of the orbit the Earth takes around the Sun, and you divide it by 100 million, then you get the height of the pyramid. That gave rise to even more speculative theories that the pyramid was not built by the Egyptians at all, but by the aliens. And I think it's safe to say that all these observations, including the one about pi, are really science fiction and not to be taken seriously. But it definitely is the case that whoever built this pyramid had some knowledge of geometry, because you would not create anything like that by throwing bricks randomly at the desert. And it is indeed the case that the difference between the angles of 4 corners are within 0.01%, and so are the distances. So the Egyptians had a good, what appears to be a good empirical understanding of geometry and some facts about volumes and areas, but there is no indications that they were interested, or anyone else at the time was interested in geometry as an abstract science, it was more empirical set of rules about computing volumes. So the correctness of these rules was measured by accuracy, and there was no need for proof. And as a consequence, the abstract objects mathematicians want to talk about were not distinguished for real things. So a line segment would represent a piece of string between two pegs or a straight path between villages. And when one talked about the volume or way of computing it, one would probably have in mind a quantity of grain in some container. So it was, it's fair to say that it was the Greeks who made the geometry abstract and formulated statements we now call theorem, which they went on to prove. And once a proof is obtained, it applies not to one pyramid or to one piece of string, but to all objects it's concerned. And good examples people would have seen or heard about is the Pythagorean theorem, which tells you that for a right angle triangle, sum of squares, a squared plus b squared equals the square of the hypotenuse c squared. And this is a theorem because you can prove it, and the proof doesn't depend on the choice of a triangle you start with. And what's really remarkable about this kind of proofs and the subject in total is that the proof can be given in a rigorous way, but at the same time without using any mathematical symbols. So here is one of many proofs. I mean, this one is actually attributed to the Chinese of the Pythagorean theorem. It's not, I'm not claiming it's obvious, so you have to think about why is it exactly that I can rearrange the triangles on the left to form the triangles on the right, and then what's left is the sum of two squares, a squared, b squared. But once you're, with a moment of thought, convince yourself that this is true, you've essentially proved this theorem for any triangle, and you use that without writing any formula. Now, before you prove theorems, you need to know what the rules of the game are. That is, you need to make some assumptions and only apply the laws of logic to these assumptions and make deductions like this. So this was another contribution of the Greeks to formalize these assumptions, and they now go under the name of axioms. And they attributed to Euclid of Alexandria. I think it's accepted by historians of mathematics that these elements, the famous collection of books Euclid wrote, which contain these axioms, is not entirely his work, but it's a work of his contemporaries and teachers. I mean, one of his great contributions was putting this together and trying to find logical framework. So what Euclid did is he, one of the things he did, is he's formulated 5 axioms, which we now regard as axioms of what we call Euclidean geometry. I'll tell you in a moment how you can depart from some of these axioms, but for now, we'll take these as granted. That was his rule. If you assume this, then everything else should or would follow as theorems. And some of these axioms are what you would call obvious. So these are axioms about geometry of a plane. Exactly one straight line segment may be drawn between any two points. A piece of a straight line, that is a segment, might be extended indefinitely to a line. Third axiom, a circle may be drawn with any given radius and an arbitrary center. And again, that's something you regard as obvious from school planar geometry. For him, it was an axiom. The fourth one is a bit odd, strange. It says all the right angles are equal. I think what this means is if you take two right angle triangles on the plane, one with arbitrary orientation, then there'll be a combination of a translation and a rotation, which will bring one right angle to another so that they'll coincide. So right angles are preferred in Euclidean geometry. And then the last axioms, Euclid's fifth axiom, also known as the parent postulate, is the following. I'm giving you one of several equivalent formulations. I say it like this. Given a line, call it L, and the point P not on this line, there is exactly one other line. This is this thinner line or a lighter line, which contains the point P and doesn't intersect L. Okay, so this is Euclid thought that this needs to be, this fifth axiom has to be added to the first four to make a complete set, but it cannot be deduced as a consequence of the first four axioms. And again, this is something I'll come back to, the relation of the fifth axiom with the first four. But you see, now once you have these five axioms, you can aim to establish theorems, and some of these theorems will be obvious, like the one I'm just going to present to you, and some of them will be less obvious, but the art now is to deduce as much as you can from these axioms. So to give you an example of how it's done, I'm going to prove that two distinct lines meet at one point at most. You see, it's not part of the axioms. I didn't tell you that, and yet it can be deduced. And then the way we're going to do it is by presenting what we call proof by contradiction, right? So it's G.H. Hardy, a British pure 20th century pure mathematicians, compared this idea of the proof by contradiction to a chess gambit. In a chess gambit, one sacrifices a piece to hopefully gain an advantage in the position later on and win the game. In the proof of contradiction, by contradiction, a mathematician sacrifices or offers the whole game. So we say, trying to prove a theorem like this, we say, let's assume it's false. Okay, so we're going to assume that it's false, and we're going to, well, use logic and the axioms of Euclid, and hopefully reach a contradiction. And once that's done, we'll have to admit that our assumption was wrong, so that the theorem is correct at the end. So, but if we assume that it's false, then the two lines meet at more than one point, at least 2 points, call them P and Q. It could be more, but let's only care about 2. Well, then by Euclid's axioms, there exist at least 2 lines through P and 2Q. These are the 2 lines which meet at P and Q. But this contradicts Euclid's first axiom. Remember, the Euclid's first axiom was that between any 2 points, you can draw exactly one line segment. So by assuming that our theorem is false and using logic, we contradicted the first axiom of Euclid, and the only way out, therefore, is that this theorem is true. So that's an example of a proof of admittedly very basic theorem. Well, then, so let's look at these 5 axioms again. So in mathematics, it's important to avoid redundancy. So if I told you something, I shouldn't be telling you the same thing, but using a different language, which in axiomatics means that the set of axioms should be, well, should be complete. If any of these axioms were to be redundant, so maybe the third one could be deduced from the second, first, and fourth, and fifth, we shouldn't have it on our list. And it was suspected from the very beginning of the subject, geometry, that this 5th axiom, the parent postulate, is actually not independent, but it follows from the first 4. So many philosophers, mathematicians, since the time of Euclid, tried to deduce the last one from the first 4. And there was another group of people who claimed that this axiom has to be added as independent, because if you don't add it, then there might be examples of other geometries which satisfy the first four axioms, not the fifth. And this dispute was put close in the 19th century, where the first example of what we now call non-Euclidean geometry was constructed. So here, by a non-Euclidean geometry, I will mean a geometry which satisfies the first four axioms, but not the fifth. And I'm going to explain this example to you, but once this is done, we will need to accept that the fifth axiom has to be added to a set of axioms, because if it wasn't, then we would have this example satisfying the four axioms, but not being the same as Euclidean geometry. Okay, and the example I'll give you goes under the name Poincaré disk, although it was, if you look at 19th century papers, it's quite clear that it was this model was discovered by Beltrami, Italian mathematician, not by Poincaré. So what is the arena of this? It's called hyperbolic geometry. Right? So what's the arena of the hyperbolic geometry? What is a disk? We can think of this disk as having Euclidean radius 1. Well, it's not very important that it's 1, but it's important that it's not some number. I'm going to tell you what on these disks replaces the straight lines. So Euclid's axioms talk about lines, which end up being straight lines in the plane. What are the lines here? And to satisfy the first, well, definitely the first two axioms, we should be able to connect any 2 points on this disk by a unique line. Okay, so there are two types of these lines. There are the diameters, like this one. So if the 2 points you want to connect lie on a diameter, then it's the diameter which you draw. If they don't lie on a diameter, then you construct a segment of a circle, and the deal is that this circle should intersect the boundary of the disk, this bounding circle here of radius 1, at 90 degrees. And you can show without too much difficulty that there is, for any 2 points on the disk which are not on the diameter, there is a unique segment of the circle which contains these 2 points and cuts the disk at 90 degrees. And so once you have these lines, you can build geometry. For example, you can define what you mean by a triangle. You can pick 3 points. This would be the corners of this triangle here. And you can connect them pairwise by hyperbolic lines, and what you create, you declare to be a triangle. Now, I'm representing my disk on, my lines on a picture graphics of the Dutch graphic artist M.C. Escher, who like a genius, was able to represent this hyperbolic geometry fairly accurately. This one painting is called Circle Limit 4, and contains a collection of angels and demons, white and black. And you see, in hyperbolic geometry, it seems that as you get closer to this boundary, these angels and demons become much smaller. And in fact, what happens is they have the same size. The same size in hyperbolic geometry if you use the notion of hyperbolic area and hyperbolic distance. So what is hyperbolic distance? Well, it's a distance which makes these lines, this kind of paths, minimum. So this is, it's supposed to be a lecture with no formula, but I think I'm going to give you a formula for this hyperbolic distance. If you don't understand the symbols, don't worry about it. How do you calculate the distance between 2 points P and Q? Well, you do the following. You produce your circle segment, and the circle intersects the boundary at 2 other points, A and B. So now you have 4 points. Now you create segments, BP, BQ, QA, BP, and these are Euclidean segments, and you construct this expression, it's a natural logarithm of a ratio of products of this segment values, and we declare this to be a distance between P and Q. Now, two things can be shown, and one of them I'll show in this mini course I'm giving here. You can show that the hyperbolic lines, which I define, circles and diameters, have a property of minimizing this distance. It's far from obvious, but it's true that if P and Q are points, and that's the distance between these points, then the path of the shortest distance is one of these circles. It can also be shown that the boundary of this disk with respect to this hyperbolic distance is infinitely far apart from the origin. So that is kind of explains why it is that the angles and demons seem smaller, they're just very far away, but they impact the same size. Now, why is it that hyperbolic geometry, proves the necessity for Euclid's fifth axiom? See, it is because it doesn't satisfy this axiom. So here's why. Remember, Euclid's fifth axiom said that if you have a line L and a point not on this line, then there'll be a unique line through this point not intersecting L. We call it parallel. In hyperbolic geometry, there are infinitely many such lines. So here's an L, hyperbolic line cutting your circle at 90 degrees, and the P not on L, and a bunch of lines, and I could have infinitely many of them with a property, but they go for P, cut the circle but don't intersect L. But you can also check the first four axioms one by one, and I think the first two I've already checked for you, to convince yourself that they hold in hyperbolic geometry. So, if it was the case that the fifth axiom followed from the first four, then the hyperbolic geometry should not exist because Euclidean geometry would be the only one. So it's independent. That proves that it's independent. There are other models where you break some of the Euclid's axioms. For example, the sphere. If you think of a geometry of the sphere, then Euclid's axioms don't hold. And it's more intuitive to think of a sphere maybe than this disk, because a sphere is like the surface of football. But it will not help you with Euclid's fifth axiom, because on the sphere, other Euclid's axioms also don't hold. Only two axioms hold on the sphere and not five. Whereas on this one, four hold. Well, let's stay with this hyperbolic geometry and ask in what other ways. So we see that it breaks Euclid's fifth axiom. In what other ways it differs from Euclidean geometry? And one such way is when you think of tiling of a plane. Right? So tiling of a plane means covering the plane with a number of identical shapes, and we can have a finite collection of such shapes, but what we want to do, so for a finite collection of types of shapes, but infinitely many tiles to play with, and we call this a tiling or a tessellation, if a whole plane can be covered by this shape without any else. And one example which would be relevant for us is this one, example of a regular tiling. You can find it in the beehive. So here we can tile a plane by regular hexagons. If you allow more types of tiles, then you have some lovely shapes. In Europe, they go under the name of Islamic tiling, but in this one it's taken from Moroccan mosaic. Both this and that have a property that they are periodic. And what that means is if you've tiled a sufficiently large region, then you can take this region, cut it and just repeat it, and and then you've covered the whole plane fine. And most tilings, including the Islamic ones, will look very complicated. They are periodic. So it might be that the region you have to tile is very large, it can be the size of Brazil, but then you can start repeating. So, you know, it's quite amazing that there are other types of tilings, and the one I'm giving you is constructed by Penrose, which are aperiodic. So you can, in this Penrose fit and fire rhombi tiling, it shows that it's sufficient to use two types of rhombi, the green ones and the blue ones, and they'll cover a plane, but in a way which is aperiodic. So, you know, it's not the case, but you will construct such a covering of some region of a plane and you repeat it, and you'll get a whole plane from it. Gives a lovely digression, gives a lovely proof of it. See, if a tiling is regular, let's say you have two different shapes, a tile plane, and let's say that it's regular and periodic, then you've covered some final region, and you can then take a ratio of numbers of one type of tiles to another type of tiles, and this ratio, well, will be a rational number, something 125 divided by 2007 or something. And because the tiling is periodic, you can then it'll extend to the whole plane. What Penrose shown is that for this type of tiling, as you're covering the plane, the number of the blue tiles divided by the number of green tiles tends to, it's called the golden ratio. It doesn't matter what number it is, but it involves square root of 5. And it's an irrational number. So if you think about it, it can be turned into a proof that this type of tiling is able. But for coming back to hyperbolic geometry and the way it differs from the Euclidean one, what will matter to us is this regular tiling. Right? Well, it can be tiled by hexagons, regular hexagons. Turns out that there are only two more ways to tile a plane by regular polygons. You can do it by triangles, or you can do it by squares, and and that's it in Euclidean geometry. In hyperbolic geometry, it turns out you can tile a hyperbolic disk, infinite hyperbolic disk, by any regular angles. So, well, why would you look at this in the first place? As because if you look at the proof, why it is that there only exist 3 regular tilings, you'll see that this proof relies on the 5th axiom. But because the 5th axiom is not true in Euclidean geometry, in hyperbolic geometry, everything is based on it you suspect might not be the case. And here is an example of such a statement. So here I'm tiling a disk with regular heptagons. They have 7 sides. They might not look regular to you. So, you know, this one is different than that one. But here the squares are the same. But this is not us being again pulled by the Euclidean intuition. These are all the same heptagons. And the reason this side seems longer than that one is because we visualized using the Euclidean distance. If you were to take the hyperbolic distance into account, they'd be the same. And there are many other interesting tilings of the hyperbolic disk. Yet another way in which Euclidean geometry differs from the hyperbolic geometry is, well, in fact, that way you can detect how the geometry departs from that of a plane is by adding the angles in a triangle. In Euclidean geometry, plane, any triangle, if you sum the angles, you get 180 degrees or pi radians. In hyperbolic geometry, turns out, and I'm defining what a triangle means in hyperbolic geometry, so 3 points connected by hyperbolic lines. If you take the angles of this triangle, by which I mean the angles between the tangents to these hyperbolic lines at the points, you'll find that this sum is smaller than 180 degrees. On the other hand, on the sphere, which is another non-Euclidean geometry, the sum of angles in the triangle is always greater than 180 degrees. So, sum of angle is a marker of how non-Euclidean geometry your geometry is. And it ties up so to kind of make it applicable to a surface of general shape. You're to the following. So take a surface of the donut. So it's kind of curved, whatever curved means in different ways in different regions. You can then define, and that's the definition, one of the definitions going back to Gauss. You can define the curvature at the point by the following procedure. You take a triangle, so you pick 3 points on this donut, and you measure the angles and some will be bigger or smaller than pi. But you see, on the donut, it will depend what triangle you take. For some triangles will be bigger than 180, for others will be smaller. So what you do is you take a limit where the points coalesce to a single point. And if you take this limit carefully, you can compute this. So sum of the angles minus 180 divided by the area of the triangle, and that gives you a number. This number will be always -1 for the hyperbolic case, or +1 for a sphere, but it's a variable number for a general surface known as curvature. So once this is very much 19th century invention of Gauss and his followers, Riemann, is curvature, but once you make sense of this, then you can say that both spherical and hyperbolic geometry differ from Euclidean geometry, not only by the type of axioms they satisfy, but also by a presence of curvature. Okay, so now I've covered 2 facets of geometry out of 4. It was the Euclidean geometry where 5 axioms hold, and the hyperbolic geometry where only 4 axioms hold. And this curvature gives me an excuse to venture very briefly into a different type of occurrence of geometry, geometry of the universe. But here I want to present it as the liberations of the curvature of the universe. So it'll be a big jump in me being vague about concepts, because it's difficult to be precise, although one can try. We talk about surface, like that surface of a disk or surface of a plane or a sphere. We say it's 2-dimensional because there are 2 degrees of freedom. 2 numbers you need to specify a point on the surface. Well, you can then talk about 3-dimensional space. And according to Einstein's theory of relativity, the universe is represented by a 4-dimensional space-time. It's 3 space and 1 time dimensions. But Einstein tells us that rather than thinking of this as 3 + 1, we must think of it together as a 4-dimensional entity. So the difference between space and time is blurred in Einstein's theory. And then once you do that, Einstein explained how this that gravity would be perceived as gravitation, so things not moving on straight lines but following some parabolic or moving trajectories, is an effect of the curvature. So he's encoded this into a set of equations, Einstein's equations, which I'm going to write down fairly symbolically as mass equals curvature. So, and that in this picture is supposed to be illustrating this. If you put the mass on some otherwise flat net, you disturb its curvature. The sums of angles are not always not 180 degrees anymore, and the shortest paths between points are no longer straight lines. They can be curved or look like curved paths, but that's only because we minimize distance. Now, so most students take courses in their master degrees or final years of undergraduate degrees just to understand the meaning of these equations. But one of the interesting very interesting theoretical developments, which is now backed by observations, is that we now know that there are regions of the universe, this four-dimensional space-time, where the curvature is infinite. And we think there are two types of such regions. One type is the endpoint of evolutions of massive stars. These are called black holes. I mean, black holes don't always form from stars. Some density or not ratios need to be saturated, satisfied. But generically they do. But this was on the theory side, awarded by a Nobel Prize, which went to Roger Penrose 2 years ago. Really, well, he didn't quite prove that black hole exists, although that's what he got his prize for. He's a very modest and honest man. So he announced after receiving the prize that he's short of proving that black holes exist. What Penrose's theorem says is that there are regions, if you believe in Einstein's equations, you take them as axioms, and you make reasonable assumptions about the type of matter in the universe, and there must be regions in the space-time which we call singularities, which are the regions with infinite curvature. Well, a black hole is not quite a singularity. It's a singularity enclosed by what's called an event horizon, so by a region surface, from inside which even the light cannot escape. So if this horizon, and if this combination of a horizon and a singularity, we call a black hole. So it is black because we cannot see it, because nothing escapes, no light can escape outside the horizon. Penrose proved that the singularities exist, but it's still not known. It's probably the biggest open problem in general relativity, in mathematical relativity, to show that if there is a singularity, it must necessarily be enclosed by a horizon. It goes under the name of cosmic centering conjecture. People working on it as I speak, but it's hard. It's one such so that there is singularities, black holes, where curvature is infinite. Another type of singularity where curvature is infinite, we think of as the beginning of the universe, the Big Bang. They're mathematically different, these two types of singularities, but they share the property that the curvature of this is infinite. And neither mathematics nor physics knows how to deal with infinities, so it's fair to say that physics, as we know, it breaks down at these singularities. But this is the third possible geometry taken up by theoretical physicists who applied to space-time and universe Einstein's equations. And to finish off, let me explain that, well, it's my favorite, the fourth facet, which goes under the name of projective geometry, but it's for us, non-mathematicians, the geometry of perspective drawing. And I'd like to motivate this by comparing two pictures, one by late medieval artist from Siena, where you see people and you see mountains and trees, and you see a tree. You not, this is not how you would see this picture in reality, because although the tree is bigger than Jesus who is being captured here, it would appear to us that it's smaller, but people are, one would really use the rules of Euclidean geometry and depict things as they are, not as one sees them. And this can be contrasted with Renaissance painting, Canaletto, where it's the interior of court in the Doge Palace. So there is this balcony here, and obviously this balcony is smaller in size than the church in the distance. But if you were to look for this balcony, it would seem bigger to you. And so that's the geometry of Renaissance painting. And projective geometry, it shows things not as they are, but as we see them. And I mean, there is some evidence that this perspective is not actually unique to Renaissance painting. You can find traces of perspective in Roman paintings, but I think it's fair to say that that Da Vinci, Dürer, the Renaissance artists, scholars, like the foundation, mathematical foundation for this geometry. So, for a mathematician, it's interesting how you capture this perspective. What is it? How do you have to modify the geometry of a plane to account for perspective, or projection? And the key object here is a horizon or a line infinity. So the arena for this projective geometry is a plane with one line attached to it, and this is the line which you see if you drive. I don't think there are such roads in Lebanon, but there are many of them in the US where you drive, that there is a road that goes for 30 kilometers or more, and you drive, and all you see are the sides of the road converging at some point. So this is a point on the horizon, maybe it's point O on the picture on the left. Well, what's remarkable is the following. Imagine not one road, but two roads. And the sides of one road merge at O, and the sides of the second road merge at Z. Now, O and Z would lie on one line. Well, that's part of Euclidean geometry, one of the Euclid's axioms. But the surprise comes if you take a third road. So the sides of this third road converge at yet another point, N. And a priori, you might think that these 3 points, Z, O, and N, they wouldn't lie on the line, but it turns out that they do. So all these points, we call them points at infinity, they all form a line rather than some curve or yet something else. So if you want to account for a horizon, it's enough to attach a line at infinity to a Euclidean plane. And that's how you do it properly. So imagine projecting one plane to another plane, from a point O. So this point O would be eye of an artist, painter, and the plane P is the plane she paints, and plane Q is the canvas. So the way this projection works is you pick a point on the first plane, pi1, called P, and you draw a line which connects P to O, and you extend it until it hits the second plane. And this is your image of the point P under this projection. Okay, and in R, this line will be just a light ray which the painter sees. Now, if you do that, you can do it with almost all points, but you'll find that there is a whole line on pi1, this line here, which is not projected to any line on the darker plane, because all the points going through this line and going through O are on one plane which is parallel to pi2. So you're missing one line. Also, there is a whole line on the plane of the canvas, which is not coming from any points on pi1. So this line here, it's not an intersection of any points on pi1 with lines going through O. And the fix in projective geometry is to enlarge both planes, both pi1 and pi2, by attaching these lines, these horizon lines, and then they are equivalent, and you can still, whatever artist you choose, wherever you place O, you can make these planes equivalent. So the lesson from here is that the projective plane is a Euclidean plane plus a line, plus this horizon line. You can then ask what, if anything, remains true in this projective geometry. For example, Pythagoras' theorem, it fails, and that's because if you take a picture of a right angle triangle and squares, and you put it on a table, and you move away from the table, you look at it from a distance, the squares will just not add up to the bigger square, and even the triangle will not look like right angled anymore. That will depend on your perspective. So in projective geometry, there is no notion of distance and no notion of area. And even there is no notion of what it means for two lines to be parallel, because that depends on the point of perspective. Turns out the notion of a circle makes no sense in projective geometry, but you can talk about ellipses. So if there are theorems or statements from Euclidean geometry which are true in this geometry, they better use ellipses, or as we call them, conic sections. And I want to finish off with one such remarkable theorem. I mean, in one sense, it's not remarkable because it's not as exciting maybe as a black hole or Escher's picture, but for a mathematician, it's quite remarkable that what I'm going to tell you is true, actually holds. It's called Brownson's theorem, and it says the following. If you take a hexagon, so not a regular hexagon, any hexagon with 6 sides, 6 vertices, and you inscribe it, or so circumscribe it along the ellipse, and then you connect the opposite points, or the lateral points, then whatever the hexagon is, as long as it's circumscribed along the ellipse, then these lines intersect at the point. And it turns out that this Brownson's theorem, and there are some other theorems like that, they don't depend on the point of perspective. So if you prove this theorem one Euclidean plane, and then you change the plane by using a projection, as I did on the previous slide, the theorem still holds. So the branch of geometry, which is concerned with establishing and proving such theorem, is it's still a very active branch because of computer vision, for example, is projective geometry. So, that keep pressing this. That takes me to the end. 4 facets of geometry: Euclidean geometry based on 5 axioms of Euclid, hyperbolic geometry where only 4 axioms hold, and things happen because you reached the last one. You can have infinitely many tessellations and angles donata up to 180. Then geometry of the universe, where you study curvature of different regions of space-time. And finally, this projective geometry, where barely anything carries over from Euclidean geometry, and that you can axiomatize. So I was vague about all 4 of these. If you want to, bit of self-promotion, if you want to read proofs, but at the level aimed at the non-mathematicians, I've tried to present them in this little book. I've gave Jihad a copy, so you can maybe you can have a look at it. If there is a library, I have another copy. I might leave it for your library, but for now I'll stop.
Maciej. Time for questions?
Yes. Yes, there is this wonderful notion of duality in projective geometry, which essentially says that if you take any statement and you replace the word point by a word line, and vice versa, the theorem remains true. And so with any statement in projective geometry, by this principle of duality, you can associate another statement. That's right. But it's interesting that some of these theorems were first proved in Euclidean geometry. And then it was realized that they're true in projective geometry, and then projective proofs were presented. It was, projective geometry is a subject which dies and is reborn every 100 years. So there was this Renaissance revolution of Dürer, Da Vinci, some others, and then it died. And And then the French school picked it up twice. So there is the Desargues theorem, Pascal theorem, and they all do with, well, with triangles, conic sections, but so that's a century later than Renaissance paintings. And this died. And then I think it was already 19th century, there was this great school of a French mathematician called Poncelet, who really proved some remarkable theorems, he and his school, about again what happens in conics. And then projective geometry before my generation, so probably before all your generations, was heavily taught at school. People would, my father would know about conics, what happens if you take a cone, you intersect with a plane, and you get an ellipse or a hyperbola, and some lovely descriptive statements. But that's gone. When my kids go to school and I see what mathematics they learn, they don't learn any of this. I think the reason is that this projective geometry as a whole is not considered useful. Useful mathematics is something like statistics. So that's what they teach at school. And geometry is, despite being really the first rigorous area of mathematics, it is dying out. So my kind of motivation for writing this book was to revitalize the subject.
Questions from students? You asked a question on WF, that was studying physics in the room right now.
Uh-huh.
A comment on projective geometry and applications in physics.
Well, it's something I'm myself I'm interested in, and it's well, there are many, and if you're those students, this become a more advanced topic, but students, if you met something called quantum mechanics, then you would have learned about wave functions and Hilbert spaces, but you'll also learn that this wave function is defined really, it's not points in Hilbert space you're interested in, a space of quantum states, but rays in Hilbert space. So you study a space of lines in the Hilbert space, rays rather than points, and this space is a projective space. There is a way of reformulating or understanding quantum mechanics as a theory in certain infinite dimensional projective space. At the more elementary level, there are, and this is something people like Arnold took interest in Newtonian mechanics, you often find, or sometimes you find pairs of potentials, which are different potentials, but when you solve Newton's equations, you find that the trajectory projectiles of these potentials are the same, and you can try to explain that. And this can be done by showing that the relevant geometries are projectively equivalent. So there is a school of thought in mechanics when you capitalize on projective geometry.
Yes, is about typing up hyperbolic is you're steering and reading figures. What about geodesic figures where this triangle squares geodesic sentence?
Well, you see, but these are geodesic because so not everything which is geodesic is regular, but everything which is regular is geodesic because the sides of this heptagon, they are geodesic.
This is my question. I mean, I don't see them. I don't see that those segments. I don't see them curved. They curved.
Or they are, they're quite small, but they're supposed to be curved. I mean, I did these images on a computer, and they are, well, so take this one. It does extend. It's a big picture. It does extend to a circle. That's the whole. Well, yeah, so this is, so a way to find geodesics is to is to aim to minimize distance. So you start with the concept of a distance, and you don't know what the geodesics are, but you say that they minimize distance. So this is a variational problem. So one approach to finding geodesics is via calculus of variation. And that's what I'll be doing in this mini course in the days to come. I'll postulate the notion of a distance on a hyperbolic disk or an equivalent of the upper half plane and solve the variational problem to find this geodesics. And what calculus of variation gives you at the higher level is a way of detecting what's called conjugate points. So it doesn't happen on the disk, but it happens in the sphere where you have two geodesics, two great circles emanating from one point, okay, and they keep emanating, but then they intersect at the antipode. And that's an effect of positive curvature, but the calculus of variation, if you study second variation, it has tools, quite sophisticated tools to tell you whether these conjugate points exist or not. There is something on chat. Please, it says, please, Hiba must be saying that, please feel free to unmute, to interact with the speaker. I'm the speaker, so I won't unmute. Okay.
Okay, so I will conclude with one last question, which maybe it's at the heart of the narrative that you presented. So we start with the concrete and build on the axiomatic with Euclid. And then the axiomatic is put to question, and we have novel geometries, which turn out to be very effective at describing physical reality again. So what do you make of this unreasonable effectiveness of mathematics? What are your thoughts?
Well, it's a deep philosophical question why it is that these theories of physics are mathematical. I mean, you could probably imagine a universe of nature where the laws of nature cannot be described or are not consistent with mathematics, but it would be an unfortunate universe to live in, because we would stand no chance of ever being able to explain it. So in that sense, we're very lucky, but we can make predictions which are then verified. I mean, so it's usually physics which is regarded as a beneficiary of this, but there is this mathematics, abstract geometry, and you can learn about black holes. But what I should maybe finish is say that it's often the case that mathematics benefits from having physics out there. So there are theorems in pure geometry, pure mathematics, proved by pure mathematicians, and the Poincare conjecture is a good example, where the tools are really provided by like Einstein's equation, and maybe you wouldn't have nowhere to start if it wasn't for physics. And one of the things this was one thing Michael Atiyah did for mathematics. I mean, he made many great contributions which awarded him Fields Medal, and probably he's earned it at least twice. But the thing he did, and starting from mid-70s, he started talking to physicists and appreciating that the geometry of gauge theory or general relativity can be useful to mathematicians in their pure theorems. So he's encouraged people to develop the language. I think this was before my time, but before mid-70s, geometers, physicists, mathematicians didn't talk to each other that much. It was Michael's mission to make them exchange ideas, and that's with us ever since.
Okay. There are no questions from the online community, so please join me in thanking Maciej for a wonderful overview of geometry. Again, he's with us for the week, and you should feel free to approach him via Hiba or other contact. Thank you much.
Thank you.